Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to continue on our midterm reviews by doing question 2 of the 2011 midterm. Now this question is really good because it really tests basically your knowledge of moments in 3 dimensions. And it tests it very, very well because it asks for basically a lot of moment questions, a moment about a point, moment about an axis, finding coordinate points to cause a moment, all of the fun stuff. So I think that the best way to do it is we're just going to jump right in. So the question itself says a rigid pipe OABC is subjected to a force, and then it gives us the nice Cartesian vector notation, which is really nice because it means that we don't have to try and solve for any of it in Cartesian vector notation. And it says that it's applied at point C, and the force P at point A. So P, we have two forces. We have force F and we have force P. Both are given a Cartesian vector notation. Very, very nice. So looking at the specific parts of what the question would like, it says, determine the moment of the force F about point O. So about point O. And express MO in Cartesian vector notation. Alright, so that isn't too bad because if I'm going to start off with here, I'm just going to put A. We know that to find the moment about a point, so we want the moment about O in 3 dimensions, the thing we're always going to turn to is going to be the cross product. And we all know that the cross product formula is going to be a position vector cross a force vector. And in this case, our force vector says it's F, and we know that we want to take the moment about point O. So let's create our position vector really quick. So we know that the position vector that we're going to use in a moment has to start at the point at which we want to take the moment about. So in this case, we're starting at point O, because that's where we want to take the moment about, and we need to go to some point on the force vector. But for this question, it's kind of easy because the force vector, well, there's only really one point that we know, and that's C. So we're going to create a position vector from O to C, just like that. So right here in this moment formula, we know we're going to go from O to C. And for looking at this, we know the force vector F in Cartesian vector notation already. So the only thing that we really need is the position vector ROC. And we know if it's ROC, it's going to be the coordinates of C minus the coordinates of O. And now this is another nice thing about this question is we know that if the coordinates of O are at the origin, so they're 0, 0, 0. So what we can do is we can effectively just cross this off because we know it's just 0. So we know that the position vector is just going to be equal to the coordinates of C. So if we were to put that into a vector right now, if we look at the x component, we're going to get negative 0.4i plus 0.1j, and then finally plus 0.2 in the k direction. And this has a position vector, so we'll have units of length, and in this case, we're dealing with meters. Alrighty, so we have our position vector in Cartesian vector notation. We have our force vector already in Cartesian vector notation. Thus, we can skip kind of right to the end and find or conduct the cross product. So the moment at O is going to be equal to, and then we're going to have to set up our nice kind of matrix. And yes, this will be very, very important. This is one of the things that if you get the final answer wrong, this is one of the first places we check to see where it could have been a possible mistake. So remember, the order of this is very important. It's always R cross F. And the second row will always be, of course, your R. So for I, we have a negative 0.4. For J, 0.1. And for K, 0.2. And then for the third row, it's going to be the force vector, which we know is 60, 70, and negative 30. So I'm going to go 60, 70, and negative 30. So this is it. I can finish this off right here. So then we can just do all the math really, really nicely. So we know it's going to be Cartesian vector notation, which is kind of interesting because the question says it wants us to determine the moment about point O and express MO in Cartesian vector notation. And that's kind of a trick because when it says express in Cartesian vector notation, you kind of get the feeling that your answer won't be in Cartesian vector notation and you have to take an extra step to find it in Cartesian vector notation. However, it's just a trick. The cross product will actually give you the answer in Cartesian vector notation. So it's kind of a cheap trick, but you know that's what they do. So if we're starting with the I component, it's going to be 0.1 times negative 30, and then minus 0.2 times 70. That's for the I. And remember, the J always starts off with the negative, so we're going to go negative. And it's going to be negative 0.4 times negative 30 minus 0.2 times 60. And that's going to be it for the J. And we can finish it off with the K, so it's going to be plus negative 0.4 times 70 minus 0.1 times 60. So we end that. This will be in the K. And we can also end the squiggle brackets and then put the units. So the force has a value of newtons. The distances are on meters. So we know that this moment's going to be newtons times meters. However, this cannot be your final answer. It's still really messy. There's still a lot of math to work out. So if you simplify it and just kind of type on all the equations in your calculator, you're going to get MO is equal to, and then we're going to do the brackets, negative 18I plus 0J, and then minus 36K. So kind of a really nice answer, and then the units will be newtons times meters. And that's the final answer for part A. So what we can do is we can actually box it and say this is the final answer. That box was terrible, but you guys are used to that by now, so it doesn't matter. So that's part A. As simple as it gets, we're just finding the moment about a point. So I'm going to go down here now. I'm going to put part B. We're going to go up and take a peek at what part B wants. So part B says, find the y coordinate of point A so that the magnitude, so magnitude will be important, of the moment of force F, so force F about segment OA is equal to this. Okay, so what it's kind of asking for, and it's kind of hidden here, but it's basically a projection is what we're going to want. So we know that MOA, or basically the projection of a force on a line, so MOA, and this is going to be a magnitude, keep in mind. So that's what we want, is going to be equal to, and what we're going to want is we're going to want two vectors. One is the moment about any point on OA, and it's really nice because if we look, we already have the moment about point O. So we can use that. We're going to go MO, and we're going to dot it with the direction of the axis that we want to project it onto. So in this case, it's wondering about OA. So it's going to be the unit vector of OA. All right, so we know MO. The only thing that we're going to be missing is the unit vector OA. And we already know that this whole equation is going to be equal to 14 Newton meters. So it's going to be a hint that maybe that the coordinate point that we're going to find will be somewhere nested in the unit vector. And that's exactly what we'll find here real quick. But let's just figure that out real quick. So let's just say we wanted the unit vector OA. We know that U OA is going to be equal to the position vector OA divided by the magnitude of ROA. And remember that this is actually really nice because the coordinate points of O are just going to cancel. So this is actually equal to RA minus RO. But we know RO is just 0 since it's at the origin. So it's just going to be the coordinates of A divided by the magnitude of ROA. All right, well that doesn't seem too bad. So ROA is going to be equal to, we're going to put in brackets, and we know it's just going to be the coordinates of A. So if we look at the x coordinate of point A, we see that it's negative 0.4. It goes back 0.4 meters. So we're going to have negative 0.4 in the I direction. If we look in the x direction, the y direction, it's positive YA. So instead of YA, I'm just going to put Y. So plus Y in the J direction. And it's on the XY plane, so it's going to be 0K. So just put the K. We know that's going to have units of meters. So we're already starting to see that we're going to be able to solve for Y because it's nested in that unit vector, OA. However, it gets a little bit tricky because we're not just looking at the unit vector, we're looking at we're not just looking at the position vector, we're looking at the magnitude. Right? The unit vector, which includes a magnitude. So we're going to have to find the magnitude of our OA, which we know is going to be the square of all the components squared. So for example, this one will be 0.4 squared plus y squared, and then there'd be a 0 squared, but we all know that's just going to be 0. That didn't turn out so well, so let's try that again. Perfect. And we can't really simplify that any further, so we're going to leave it like that, and what we're going to do is we're going to say that UOA is going to be equal to, we're going to put the brackets here, and then we're just going to divide each component by that factor. So the first one's going to be negative 0.4, and that's going to be all over the square root of 0.4 squared plus y squared. And put the square root up, and that's just in the I direction. And then we're going to go plus, and it's going to be y all over all this crap. So we're going to go 0.4 squared plus y squared. And that right there is in the j direction. So we're just going to throw in a j. And we know that there's plus 0k. So you can already see that this is getting actually kind of messy. Not really a huge fan of it. So let's just see, maybe something will cancel out. So we have our moment vector now. We have our unit vector, so we can continue with the dot product. So for the dot product, I'm going to put the magnitude of MOA. You know, it's going to be the dot product, so it's going to be the x component times the two I components. So if we look up at the vector, or the moment vector, we got negative 18. So we're going to have negative 18. And we're going to times that by the I component of the unit vector. So at the bottom, we're going to have all that gross stuff. So we're going to have 0.4 squared plus y squared. And it's all going to be divided, on the top, they're going to be negative 0.4. And for the next one, if we look up at the j component for the moment, it's 0. So we know that the next one is just going to be 0. And if we look at the I component, there's an I component in the moment, but the unit vector's I component is 0. So this will also be 0. So as we can see, some of it kind of canceled out pretty nicely, so it wasn't too bad. So if I were to multiply the 18 into the 0.4, what I'm going to get is 7.2. And then of course this will still be divided by all that stuff, so it's going to be 0.4 squared plus y squared. Let's straighten this up. And remember that all of this is going to be equal to 14, because it's going to be equal to the 14 newtons per meters. So it's nice because we have one equation, and our only unknown here is going to be that y, so we can start solving for y. So the first thing I would do is I'm going to bring all that stuff at the bottom, the square root sign, to the other side, and I'm going to move 14 to the bottom of that side. So what I'm going to have is the square root of 0.4 squared plus y squared is equal to 7.4 divided by 14, which is 0.514. And I can carry the square root over. So the next logical thing to do is, well, let's get rid of that square root. So we'll square both sides, and what we'll get is 0.4 squared plus y squared is going to be equal to 0.264. All right. So now we can move the 0.4 to the other side to get y squared is equal to 0.104 And then finally we can square root both sides to get y is equal to 0.323. And this would have units of meters. And that's what the question wanted. It wanted that y coordinate. So that's the magnitude of the moment projection. It will be 14. And that's exactly what we solved for. So let's just double check, find the y coordinates. So that the magnitude of the moment of force F about segment OA is 14. So we're good to go. Part B is now done. So now we can go on to part C. Part C is actually a very good question. It's one that actually tricks a lot of students because you're not taught it very well, I guess. It's not that you're not taught it well. It's more, it's a kind of an abstract sort of thing. So express MOA in Cartesian vector notation. So it sounds pretty obvious, but it can be kind of hard. So one thing that we know is this. The magnitude of MOA is going to be equal to 14. So that's good to go. The one thing that we don't really know is MOA as a vector. MOA. But we know that we can find a Cartesian vector notation if we know the magnitude, which we do, times the unit vector of its direction. In this case, it's going to be OA. We know that it's going to be in that direction, OA. However, if we look up at the unit vector, we actually have it already solved. The only problem is we got to substitute the value of y that we found, so the 0.323, up into this equation. So I'm going to highlight this equation with a little pink arrow. So we're going to substitute y into there to get our complete unit vector that doesn't have a parameter in it. So what's going to happen is this. After substituting y, you get UOA is equal to, I'm going to put the squiggle brackets, and it's negative 0.778 in the I direction. And then plus 0.629 in the J direction. And plus 0 in the K direction. So now what we can do to find the moment MOA is we're just going to take that 14 and multiply it by every term in that unit vector. So it's actually not too bad of a question. So what we're going to get is MOA as a vector is going to be equal to negative 10.9 in the I direction plus 8.8 in the J direction and plus 0 in the K direction. So we're going to end the brackets. Remember, this will have units of newtons times meters. And it's very important that you remember the units in the midterm. Very, very important. You get lots of marks taken off otherwise, because units are one of the most important things in engineering. So then again, just to kind of clarify, if some people are, oops, that's not what I wanted to do. So what I want to do is just clarify for some people that are wondering, hey, maybe where did you get this 10.9? Well, that's going to be the 14 times by the unit vector of x, which is the negative 0.778. So that's the question. Very, very short question. The only thing we had to do was find that unit vector, but it also creates a problem because let's just say perhaps that you get the y coordinate wrong. Well, then your unit vector is going to be wrong, and then your MOA will also be wrong. So I'm not sure how the markers will account for something like that, but it's very important that you know what you're doing all the way through, or else it's hard to get part marks later on. All right, so finally the last question says replace the forces F and P by an equivalent force and couple moment system about point O. So I highlighted this whole question because it's actually very straightforward, very, very nice. So we have two forces on the system. We want to turn them into a single force, and then we also, because we're moving forces in a three-dimensional space, we have to account for the moments that they create. So what we're going to have to do is take the moments the moments created by F and P about point O. But it's nice because in part A, we found the moment about O created by force F. So the only thing that we have is the moment that P will create. And the moment that P will create, So I'm going to put this as m at p. This is very, very interesting because you can do it with the cross product. It'll work fine, and actually it's pretty easy. But what we can see is this. P runs with the x-axis. So P will not create a moment about the x-axis. P also intercepts the y-axis. So it'll not create a moment about the y-axis. So looking at this diagram, the only time P will create a moment is for the z direction, the z-axis. And what we can do is we can take the magnitude of P and times it by its moment arm. So even though it's a 3D case, we can make it into a 2D case to kind of make our lives easier. So if we're looking at P, we know that the magnitude of P, according to the question, is 30. So what's going to happen is we're just going to put P is equal to 30, and then we're going to have to times it by that distance. And if we look, and sure enough, as luck would have it, the distance, the perpendicular distance between O and P is going to be this red line right here, which is y of A, which is something we had to solve for. So we got it as 0.323. So it's going to be 0.323. And when you throw that in your calculator, what you're going to end up getting is negative 9.7 newtons times meters. And I kind of blew it, but what you get is 9.7. And then you're going to have to ask yourself, okay, well, is this going to create a positive or a negative moment? And if you look at force P, we can kind of see that it's doing this tendency around the z-axis, which is a clockwise rotation. Therefore, this will actually be negative. So a negative 9.7. And then again, what we're going to want is we're going to want it as a Cartesian vector, so we can add it with the other one. And we know that it's going to be 0i plus 0j. And then, of course, it's going to be finally negative 9.7 k. That's going to be units of newtons times meters. So remember, if you have a force that acts in a plane, the moment created will be perpendicular to that plane, which is what we see here. This is in the xy plane, therefore it creates a moment about the z-axis. So our resultant moment for these two is just going to be m1, or I guess mo plus mp. That's how I labeled it, but it's just basically both of the moments created by those forces about 0.0. So if I add them together, I'm going to get a nice vector. So I'll put mr. And what it's going to be is negative 18i plus 0j minus 45.7 k. And we can end the brackets instead of units of newtons times meters. And we can do the same thing down here for FR, because we know that FR is going to be equal to all of our forces put together. So it's going to be F plus P. And it's very, very simple because both of those are already in Cartesian vector notation. So we can just add up all the components. So FR is going to be equal to 90i. So I'm going to do the squiggle brackets. 90i plus 75j. And then finally minus 30k. And the squiggle brackets and units of force, so I'll have units of newtons. I'm just going to make this j look a little nicer because it's pretty gross. And those are our two forces. So the one thing that we need to do too, it's a final answer. Give it a nice box to let everybody know, hey, this is the final answer. And remember, we need two final answers. We need a resultant force and a resultant moment. So this is what we get right there, MR and FR. And all you have to do that is just sum up all the moments, sum up all the forces. So question 2, very good. Really test your knowledge of moments, but once you get the hang of it, you should be able to solve it pretty fast. So thank you guys so much for listening, and I will see you guys at question 3 on the 2011 midterm.